Okay, so now let's look a little bit deeper into how to connect to the number of particles. We referred to moles and millimoles previously, but how do we, in practice, get this number of particles off of something like the periodic table? Well, there's no way to know the number of particles unless we know two things, and that is the mass of what we're dealing with and what are the particles themselves. If you don't know both of those things, you're not going to be able to know the number of particles. And this is kind of like saying, well, how many grapes do we have in a bowl of grapes? In order to make that calculation, you need to know A, what's the mass of the grapes that exist in the first place, and B, how much mass does each grape have? Otherwise, you couldn't calculate the number of grapes that are involved. The same goes for atoms, and more so because we can't just count them with the naked eye. And so when we look at the periodic table, and this is just a little clipping of the periodic table to show the top right, which is the part you're probably going to use the most, the atomic mass of each element shows the mass of a mole of particles. And so when we look at this, right, we look at carbon, it says 12.011, and there's no units that are associated with this on the periodic table, but because we know how to use the periodic table, we know that 12.011 means that that is the number of grams of 1 mole per carbon. Always 1 mole, right? 1 mole of carbon weighs 12.011 grams. And that means that a millimole of carbon has a mass of 12.011 milligrams. We've just made both units milli, and the numbers are the same. 1 mole of oxygen, 15.999 grams. 1 millimole of oxygen, 15.999 milligrams. This atomic mass shows the number of grams per 1 mole of this element. Okay, what about sodium chloride or other compounds? Well, we know that it's NaCl, right? That's the formula for sodium chloride. In order to get the mass, the formula weight of sodium chloride, the compound, we recognize that sodium has a formula weight, an atomic mass of 23 grams per mole. And we look at chloride, and it's got 35.5 grams per mole. And I highly recommend that you use your periodic table to verify for sodium and chloride that this is the case. If sodium is listed as like 22.999, between friends, 23, that's just fine for this course, makes the numbers simpler. If we want to get sodium chloride, well, it's 1 sodium and it's 1 chloride. So let's just add up 1 sodium and 1 chloride. It's 23 milligrams per millimole plus 35.5 milligrams per millimole. Sodium chloride, which again is both a sodium and a chloride, has a mass of 58.5 milligrams per millimole. And here, go ahead and do a little practice. Pause the video for a second and try to calculate the formula weight of CO2 and of H2O, right? Use your periodic table, see if you can come up with an answer, and we'll see what you get. Okay, hopefully you're able to pause and give this a try. CO2 comes to about 44 milligrams per millimole, H2O to about 18 milligrams per millimole. And again, we could report these in terms of grams per mole, but in terms of healthcare, we use millimoles quite often just because it gives us more of a counting number to deal with rather than a fractional number, as a mole is still a rather large amount of substance. So we're going to generally use millimoles when we can for this course. Okay, so how do we calculate moles or millimoles from a given mass? And here I've included a couple of formulas, right? If you want to get millimoles, you take the mass and you divide by the formula weight. If you want to get the mass in milligrams, you take the millimoles and you multiply. But really, I would not try to memorize both of these formulas, and these will not appear on your equation sheet. What I think is really important is to use formula weight as a conversion. We've dealt with dimensional analysis, and we can use what we've learned to deal with formula weight as a conversion. So let's look at this question. How many millimoles in 12 milligrams of sodium chloride? And we should have enough information to get this because we know the total mass, 12 milligrams, and we know that what we're dealing with is sodium chloride, and we know the mass of that. The molar mass, I should say, or the formula mass is 58.5 milligrams per millimole. So we start with what we know to this problem, 12 milligrams, multiply it by 1 millimole over 58.5 milligrams. The milligrams cancel, we'll be left with units of millimole and 0.205 millimoles of sodium chloride. Again, just like we saw the concentration able to be used as a conversion, so too is this formula weight. 12.0 milligrams of sodium chloride contains 0.205 millimoles of sodium chloride particles. Okay, one last thing we want to look at is in addition to millimole, we also look at millieq. And so this is milliequivalent and it considers the charge, right? What is the total charge from these electrolytes like sodium or potassium? And this matters because sodium and potassium, they each carry a +1 charge. We learned that from the periodic table. But other electrolytes may contain a +2 or even a +3 charge. And so often we want to track not just how many particles, but how much charge exists from this particle. And it's a pretty simple calculation. You get the millimoles, you multiply by the charge that that particle carries. And for a couple of examples, let's say we have 1 millimole of sodium plus. We know that that has 1 millieq because 1 millimole of sodium contains 1 millieq of charge. If we have 5 millimoles of sodium, you simply multiply it by the +1 charge on the sodium, and we would know that 5 millimoles of sodium is 5 milliequivalents. That's the charge that's floating around from that sodium. If it was 1 millimole of calcium, well, this is a +2 charge, so each millimole of calcium gives 2 milliequivalents. And therefore, if we had 5 millimoles of calcium, we'd have to multiply by that +2 charge to describe that it's 10 milliequivalents of charge associated with that 5 millimoles of calcium.